Hi, everyone. My name is Abi. I'm going to talk to you about our project called Software-Defined Radar Testbed for Multi-Target Tracking. This project is in collaboration with Drexel Wireless Systems Lab, as well as Lockheed Martin's Advanced Technology Lab. For radar and multi-target tracking, these are very important tools in future autonomous systems. When you look at ideas like sensor fusion, which use radar along with LiDAR and camera, radar plays a very important role to be able to detect vehicles and pedestrians in difficult weather conditions. Through the use of tracking filter, radar systems track the trajectories of multiple vehicles and pedestrians, given noisy measurements from sensors. As you can see at the bottom, you can see some examples of how a radar could be useful for a vehicle traveling down a street. So you can have multiple different vehicles that are nearby. You could have pedestrians walking close to the car, and the tracking filter and radar system would be able to alert the driver, or even just stop the car automatically when a car or a pedestrian gets too close. The vision of this project is to basically combine the ideas of software-defined radar and channel emulation to be able to create a sort of a framework to build a digital twin, to be able to build more intelligent multi-target tracking filters and have large-scale repeatable wireless channels that can represent different radar environments. So why software-defined radar? So I'll talk a little bit more about software-defined radio, which is used in this, but just more broadly, being able to adjust factors like modulation, center frequency, and bandwidth is very useful to be able to evaluate tracking filter performance on different sort of influences and factors. And additionally, to be able to have a sort of scalable system, which can have timing synchronized radios is also quite useful. For channel emulation, the general idea is that we want something that's a bit more affordable to expensive field testing. So being able to create very complex environments and quickly put them into a testbed sort of environment is sort of a way to make a software-defined radar think it's operating in some environment, even though it's not actually there. So it exposes real radio hardware to realistic indoor and outdoor wireless channels in a controllable and repeatable manner. And finally, this idea of creating a digital twin is useful because if you want to create an intelligent tracking filter that's maybe based on machine learning approaches, then being able to create large amounts of training data that are accurate every single time, repeatable, it's also not very expensive to be able to create this. This is where this idea of combining these two elements together is very useful. You can see a couple of pictures on the right-hand side where we look at a bridge in Philadelphia, which on the top is defined in a ray tracing tool, and on the bottom is defined, well, in real life. And what we'll show later in this PowerPoint is that we could sort of create a radar environment through ray tracing and have it sort of resemble sort of real-world experimentation. So to do this, we leverage the Drexel Wireless Systems Lab. Drexel has a large-scale software-defined radio testbed, and I'll cover some of the key elements of this testbed. So on the left-hand side, we have sub-6 gigahertz and millimeter wave antennas. We have ray tracing and channel emulation tools. So in this case, we used Remcom's Wireless Insight. And on the center side, we see software-defined radios, which have, there's actually a grid of them in this lab, which basically are all remote access and controlled to a remote PC that it's quite, it makes it quite convenient to be able to access in and perform experiments. And we also have a timing synchronization tool that's used for all of the different radios to be able to have a lot of scalability in the future. So first, I'll talk about over-the-air experimentation. There are a few terms here that I highlighted in red. I'll just briefly explain what they are, just to kind of be clear about the terminology. So starting over the air, the USRP is a popular type of software-defined radio The GNU radio, GNU radio is the type of signal processing software that's very commonly paired with USRPs. Octoclock is a timing synchronization tool that is provided by the same manufacturer of USRPs. And then while this isn't over the air, but for when we talk about channel emulation, the DYSE is the name of the tool that we use for that. Just on a high level for over the air, we want to basically feed in a real world environment, use one of the antennas that we have, feed it through a software-defined radio, which basically provides real world measurements and generates range and velocity values. And then we'll basically plug these into a tracker to perform some filtering. So software-defined radio as radar is useful because it has many of its physical layers functions programmable by software. So things like modulation, bandwidth, and center frequency can be rapidly adjusted. Sort of a limitation is that the bandwidth is limited in software-defined radio, but the ability to be able to configure these radar environments and architectures to be able to test algorithms, at least at an initial stage, in a rapid manner, sort of is what helps weigh out the limitation of the limited bandwidth. When paired with signal processing software, like GNU radio, there's actually these external libraries that can be brought in that provide the functionality just through different software blocks to provide radar functionality for software-defined radios. So for our project, we used a toolbox called GR Radar. So GR Radar provides the ability to get real-time range and velocity measurements. And then the output of these measurements then can be parsed and then analyzed by various tracking filters. So first, we wanted to do a baseline test just to verify that GR Radar works. So here we basically got the software-defined radios, which are hooked up to two different sub-6 gigahertz horn antennas to operate as a radar. And you can see that there's a pedestrian moving back and forth. And this software-defined radar is able to create real-time detections that represent accurate range values of how far this pedestrian was moving. One thing to note is that these are real-time measurements, but when we eventually use a filter, we'll start to go more into post-processing. So now that we verified that the SDR works as a radar, we wanted to now add a different target to the environment. So we have a second pedestrian moving in an opposite direction. And you'll notice these pedestrians are holding an object. This object is actually a copper plate that has a high RCS value. It's to be able to have some more detections, especially at the later, like the further distances. Since this isn't a perfect environment, there's a lot of interference from metal objects in the lab. This kind of helps solve that problem. What you could see at the bottom is basically in the green dots are the raw measurements over a finite period of time. And then you can see the two tracks. So the orange and the blue represent tracks 1 and 2 of each pedestrian. And this is actually exactly what you want to see, because you're able to sort of get these accurate trajectories just by feeding it the raw measurements. So the final thing that we wanted to do was now actually add a second component, is have multi-target tracking, but now also have this happen at millimeter wave. So millimeter wave is very popular now for autonomous vehicles because you can have, because of the small wavelength, you're able to get more, like fine-grained measurement accuracies just due to the small phase changes. So we wanted to do the same experiment at millimeter wave, and we were able to show that using a 28 gigahertz up converter and down converter, and using the JBDA again in post-processing, we're also able to get accurate detections. So between 0 and 8 meters, we can have this oscillatory movement that go back and forth. you can see a video at the bottom of what the experiment looked like, and then and what the sort of antenna system sort of looked like as well. So I want to talk about the emulation now. This is at the bottom, where basically the goal is to be able to feed in a environment representing a bridge, so something that a vehicle might be on, and then feed this into the same pipeline that we have of the software-defined radio, the tracker, and just the WSL grid. Oops. So I mentioned the DYSE that we use for emulation. This stands for Dynamic Spectrum Environment Emulator. It basically has software-defined radios inside of it. So it has 24 SDR nodes organized in a full mesh. So by doing so, you can support up to 576 different wireless channels, each at 100 megahertz bandwidth. And what's unique is we actually have a software that it's new that basically converts the output of ray tracing. So let's say you have channel impulse responses of a bridge and an antenna on that bridge. You can basically convert that now into the configuration to be able to power this or function the DYSE. And it's a quite straightforward process that lets you go back and forth very easily. As a sort of baseline experiment, we wanted to, if you remember the over-the-air multi-target tracking, we wanted to do the same thing. We know what the output looks like. Like we know that when you have two people walking back and forth in the lab, the result you're going to get is sort of this oscillatory movement where each goes in sort of the opposite directions. And that's exactly what we did. So it's a very simple experiment here where we have a target moving one direction and another target moving the other direction. And we're able to get the same sort of result that we got in over the air. One thing to note is that the range values are not exactly accurate, and that's okay. The goal here is not really to get the most accurate range values, but really just to make sure we can get the trajectory values sort of in the most like accurate motion that was there in the experiment. So now we're kind of at the main goal that we're trying to achieve is basically plug in a very complex environment into this radar system, the software-defined radar system. So we represent the Ben Franklin Bridge as through ray tracing as various different building materials, and have a couple of antennas that represent the radar, have different targets moving back and forth, so two targets moving in opposite directions. And then we generate the impulse response and feed this into our overall testbed system. And you can see that the output that we get is actually, it represents the tracks that we were hoping for, right? You can see the, as track one goes closer to the radar, track two moves further away. But you'll notice that it's a little more noisy and it's not as smooth. And this is okay. And this is actually sort of the point that we're trying to build with this testbed is if we can sort of challenge the tracking filters to have trouble with certain scenarios. Can you now start improving the tracking filter and make it more robust and try it out again? And if it works well, then make it a bit more complex and then try it out again. And it's sort of this back and forth cycle that now is very straightforward to do with our testbed, as opposed to having to do this expensive field testing each time. So in conclusion, this really is kind of it's a good tool that can be used for emerging technologies like autonomous vehicle radar. This idea of large-scale channel emulation through repeatable experiments works very well with our SDR testbed. You can have both over-the-air, but also emulated experiments that help you prototype and improve your multi-target tracking filters. And I think generally our future work is really going to be to leverage this idea of channel emulation further and kind of tackle two things. So one is try to see if we can get this to also work at millimeter wave. And then also we want to be able to get this tracking filter to work in real time and not have it be something that we do in post-processing. That's kind of it. So if you have any questions, please feel free to email me. I'd be happy to talk further. Other than that, thank you very much for your time. I really appreciate you listening to this presentation.